Josie Hodges, and this summer I did a project in the study of diodicity of fluidic diode injector designs. So this basically, I came up with my own designs, and with help from Dr. Zhu and a couple of other previous design ideas. And I modeled injectors and tested them. So I had, there we go, 3 main goals with this project that I divided the work into. One was to design injectors that I believed had a chance at reducing backflow. The plan to accomplish this was to use 3D modeling software. The next step was to test the injector designs and measure flow rate and pressure drop across each injector in the forward flow direction and backflow direction. To do this, I used a simulated test in the fluent simulation software ANSYS, as well as real-life testing with pressure transducers and water hooked up in tubes to the injectors themselves. And the final and most important goal was to use the measurements to calculate the diodicity of each injector, which is a sort of efficiency measurement of each injector at reducing backflow. So this was kind of my schedule for the project. I spent the first few weeks learning ANSYS, the software, and then reading literature on previous kind of experiments and work and research done in this. And then I spent time in ANSYS creating the designs and testing them, and then actually testing in the lab and writing up the results. So just some definitions that might be helpful for understanding what my project was. A fluidic diode injector is an injector device with no moving parts. The idea is that it experiences high flow resistance in one direction and low flow resistance in the other. Backflow is the unwanted fluid in the reverse direction, and this is what I was trying to reduce in my injectors. And diodicity, the measurement I'm taking from all of the data, is the ratio of the pressure difference in the backflow direction to the pressure difference in the forward flow direction. I focused a lot on diodicity to compare pressure drops across each separate injector in my project. That's kind of how I got all the information I needed. So applications of this project. Linear detonation engines using pulse plasma discharges are being studied for the use in rocket engines, jet engines, and ground-based gas turbines. The reason why it's important to reduce backflow in these fuel injectors is because it can be very dangerous for these engines. The fluid building up can cause explosions and fires, and this is kind of, it opens the gateway to more research in this field if we can keep this safe and usable across all research. Yeah. So these are my designs. I'm going to move this window that I tested. I came up with 5 designs and then 1 got cut, and I ended up with 4 overall. These are the 4 that kind of survived every aspect of testing and seemed to work pretty well. So I used the tree design, which is this first one up here, as a sort of control group, like in an experiment. I didn't have high hopes for the pressure drop difference, but it's the type of design that's been used by many people before me. And I thought it would be a good start and kind of be easy to refer back to when looking at the other designs. The Pacman design right here was recommended by my mentor, Dr. Zhu. And it, you can kind of see how the fluid would behave in both directions. In one direction, it would get caught in these kind of, I guess, horseshoe type shapes, this little stop. And in the other direction, it would flow swiftly over it, kind of like a wing on a plane. And so that was the idea behind that. And it, so I thought that one would work well. And then from that design, I had the idea for the duck feet design right under it, which is just kind of an increased Pacman. It's a little more, intricate. And I thought if Pacman works well, then this design should work well too. And then the final design, the Snail design, I kind of put together by looking at other research done by other people and how they kind of simulated the flow. And I thought that this would be the best way to get the water flow to turn in on itself. So it kind of shoots it back at itself, slowing it down in the backflow direction. You can see that. And so these are the designs that I thought would work well. And once I had them kind of set up in ANSYS, I moved on to modeling them and setting up actual simulations. So ANSYS. This is a multi-physics engineering simulation software, which is a mouthful. It can be used to create 3D models and then test them under different conditions. After creating the designs in SpaceClaim, which is ANSYS's kind of 3D modeling software, it's like CAD or Solid Edge, I needed to generate a mesh of the model in order to evaluate and perform calculations at many, like thousands of different points across the model. So it kind of splits it up and it performs the calculations needed at every piece of the actual design. So after generating the mesh, I used ANSYS's kind of settings to set up the water pressure at 50 meters per second and kind of other generic setups like the room temperature and density of water, little pieces that it needed to know. So there are many different layers of settings in ANSYS, and it's too many to really get into deep in this presentation, but I focused on the Fluent software because that's the kind of testing I was doing. And everything was mostly set to just generic conditions except for the actual water pressure and what would be influenced by that. So I used, for the actual simulations, I needed a time step of around 4,000 with a step size of 0.0001. It was kind of trial and error getting these numbers, and it was just the amount of times it iterated upon the calculations. I tested each injector in the forward and reverse directions, which is kind of, you can see it would be from one direction and then the other in this design. This is the mesh here, which was set up for the actual calculations. So here are some results from testing that particular design. On the left, you can see the forward flow, which would go from right to left. And the right design is backflow from left to right, which is a little confusing, but you can kind of see where the pressure starts out and decreases over time. And these are the results of that pressure difference. The ANSYS simulations would only converge at very high pressures. So that's what's seen here. The greatest pressure difference was the duct feed design, which was very interesting to me because I kind of expected either the Pacman or the Snail designs to be closer. Overall, the results were very positive as the backflow always had a greater pressure drop. And that should kind of be seen here. Backflow is always much greater than the forward flow at these high pressures. So that was kind of a positive reading, very good results for initial testing. And this led to high diodicity readings, which led me to conclude that I was ready to move on to real life testing and move on to 3D printing these actual injectors. So there's the diodicity readings here. And the idea is to grade it greater, since it's a ratio and you want backflow to have a much greater pressure drop and the ratio is backflow to forward flow. The idea is to get it above 1, the diodicity reading. So these were all very positive diodicity readings that I needed. Okay. So right here on the top right, you can see one of the solid edge designs. And I needed to use Solid Edge for this so I could 3D print the models because you can't directly 3D print from the ANSYS 3D software. And because you also can't transfer ANSYS designs out of ANSYS into Solid Edge, I needed to recreate them in Solid Edge. The ANSYS designs are inverted where what you create is the path that the fluid will flow in. So you would need to find a way to invert that in a different software. So instead of trying to find that, I just recreated each design in Solid Edge. So that's the tree design again here, and that's it finally 3D printed. I also added a indent for an O-ring, which is this large dent running around the edge of the design. It was put there in order to seal the injector with a plastic cover and clamps to kind of keep the water in and keep the design from leaking or spraying any water while I was doing the testing. The bottom picture is the finished and printed 3D design. And it's a little hard to see here, but that same indent was printed pretty well by the 3D printer. These plastic tubes I epoxied in afterwards so I would be able to connect the water flow to the injector design. Okay, so right here is kind of my setup where I tested the injectors. You can see the injector there with the black O-ring and the indent running around. And I would put a plastic cover on top of that and clamp it down with a couple of clamps and screwed in clamps too. And yeah, that's how it kind of set up. And then these tubes are connected to a pressure inducer. And this measures the pressure at the beginning of the injector and after the fluid has passed through the injector, the pressure of the water then. So to take these readings, I would run the pressure through the injector, and I had LabVIEW code set up that told me the pressure at the beginning of the injector and the end, and I was able to calculate the pressure drop from that. And when I needed to measure in the other direction, I think this is set up for forward flow. When I needed to measure backflow, I would just unplug the injector, twist it around, and plug the tubes back in, and I could measure for both sides. This little knob here controlled entrance area of the injector, and so I measured each pressure at 4 different entrance areas. And it was basically 25%, 50%, 75, and then 100% of the possible pressure I was able to get readings from, which is a little confusing, but hopefully it'll make more sense when I present my results. This right here, this jug on top of the scale is how I measured flow rate. I would time the amount of water flowing out of the injector into that jug, measure it, and be able to find flow rate from those calculations. Okay. An immediate problem I had was that the 3D prints were not watertight, and they were leaking a lot of water and collecting a lot of water, which really was messing with results. So to fix that, I just sealed them with paint on water sealant, and we were good to go. Okay, these are my results for testing the tree design. And it's a lot of information at first, but I was able to see that the pressure drop was greater for forward flow, which was the opposite of what I wanted. After this, however, pressure drop in backflow is greater at the higher pressure. The higher initial pressure is what caused the results to kind of lean into what they were supposed to be as it increased. At first, it wasn't what I wanted, but after that, it gradually became a greater pressure drop. This was a little confusing, and after looking at the rest of the design's results, I kind of concluded that this seems to be a problem of not having enough pressure, because you can kind of see for each design, the pressure drop is, this is Pacman right here, and the pressure drop is greater in the backflow direction at a higher pressure. The further we go up, the more the results start to look like what I predicted and what ANSYS predicted they would look like. This one's a little more back and forth, but again, the highest pressure has the highest backflow pressure drop versus forward flow pressure drop. And like through that, the higher diodicity reading. For the duct feed design, we have kind of the same, it's backward and forward, which was not expected based on ANSYS results. I thought this one would do a lot better. And I had the same kind of problem for Snail design. They all have the higher pressure at the end in the backflow, but not when the pressure is just starting out. At like 25, 50% opening, the pressure is not what I expected, but as it increases the results look a lot more like what was predicted. So that's the fourth design there. And here are the measurements for flow rate. And another problem that I had was the percent of area was remeasured every time for each injector. So those are as close as I could get. And so the beginning flow rate in forward direction should be around the same every time, and it pretty much is, but there's a measure of human error in that from having to remeasure it for each separate injector. So there's a small error there, but yes, there should be a lower flow rate in the backflow direction than the forward flow, and a higher flow rate. And so that's seen in most of them at the higher pressures, at like 25% and sometimes 15% entrance area. That's not what is seen. You can see here in the pack flow design, it's this one's a lot better. Has a much lower flow rate in the backflow than forward flow direction, except for the beginning. And then I think the same is the case in duct design. It's they're a little bit back and forth. And then in the Snail design, again, you can see a little bit, these are a lot more similar, but still a little bit back and forth. And so this is not exactly what I needed to see, and could also be caused by the entrance area error or the fact that I needed a much greater initial pressure across all the injectors. Okay, so from these types of testing, I'm confident that in the duck feed and snail design with a much higher pressure, there might be more accurate results and a lot higher diodicity readings. Here's the final average diodicity readings of each injector. So for the tree and snail design is lower than 1, which was very unexpected and not what ANSYS predicted. Pacman and duck feed designs were a little bit greater than 1, but not especially larger. And so not exactly what I needed to see, but they had promise. And I think at higher pressures, they would be able to increase a lot more. Okay, so here are kind of sources of error. I've talked about a couple of them so far, but there was still water escaping the 3D prints after the water sealant, and it was around where the tubes entered and into the 3D print itself. So that could cause a small amount of error there in pressure readings and flow rate. One of the bigger problems was entrance area, which I've said before. I had to line up the lever with a ruler to try and get the same amount of opening each time. And I believe by hand we were as accurate, I was as accurate as I could be with that, but there is human error involved in that. Another problem, which I think caused a lot of the varied diodicity readings, is the space between the 3D print and plastic cover caused by the O-ring seals. And this provided a lot of space for the water to fill that was not the actual injector and that is not accounted for in ANSYS at all. So that causes water to be able to just flow right above the injector. And it's not the majority of the water, but there's a good percentage of it that's maybe around 20% that is going over the injector entirely, which could really mess with my results. And then across all the injectors in the whole experiment, pressure needs to be a lot higher. I believe the high pressure that ANSYS required to actually converge is comparable to the actual testing in real life, and that the pressure needed to be a lot higher to see distinctive results. And so those are some possible sources of error that could have come with this experiment. For future research in this and future attempts that I might do, I would suggest sealing the plastic cover directly to the injector. The O-ring caused, it reduced a lot of leaking problems and a lot of problems with the water coming out of the injector, but sealing the plastic cover directly onto the injector with some kind of epoxy or a new kind of sealant would solve the problem of the water flowing over the injector, and that would probably clear up a lot of their results. 3D print settings that might help keep the injector more watertight, and maybe another sealant would help at keeping the water inside the injector, because that was still a problem at the end. It wasn't enough of a problem to stop testing, but there was still some water leaking out at points. And then using a more highly pressurized fluid source would probably increase the accuracy of the project by a lot. So I would recommend that for sure. I'd like to thank the Alabama Plasma Internship Program for the opportunity to work on this project, and the National Science Foundation for the program, and my mentor, Dr. Gabe Zhu, encouraging me to apply and guiding me in my research. And here are my references for the project. So there's a couple ANSYS videos and journal articles I found on this type of research that helped me put together designs and set up my experiment. Thank you so much.
Hi, my name is Flasmy, and thank you for watching this video. Make sure to follow us on our social media at CPH2AL on Facebook, LinkedIn, and Instagram. Bye!